Okay, so this second part is about how to compute probabilities and expectations with respect to our posterior distribution, so the distribution that defines a Bayesian model. And I'm going to talk about one way of doing that called Markov chain Monte Carlo. It is not the only way. It is a way I particularly like, but there's other ways. And yeah, so I don't want to give you a false impression that this is the only way to address the problem. So again, we're interested in recovering an unknown image x. We don't observe x, we observe y. And we agree that we're going to model the relationship between x and y with a statistical model, basically with a conditional distribution of y given x. And recovering x from y is ill-posed or ill-conditioned, so it's not an easy problem. And what that means in plain language is that there's a lot of uncertainty about x after observing y. So I can't really tell you what's the image that generated the data. So if I had this kind of model, for example, and A was badly conditioned or rank deficient, then clearly I can't recover y from x. Right? If, for instance, y is dimension 10 and x is dimension 100, it doesn't work. So what I'll do is I'll use a prior to reduce uncertainty and deliver meaningful estimates. And formally, I'll write some expression for p of x, and that will define a posterior distribution through Bayes' theorem, the formula here. And this will be a model for x after observing y. And in this talk, I'll consider that this distribution is log-concave. So that means that x given y is the exponential of minus some potential function phi that is convex. And z is the normalizing constant that makes this a proper probability density function and not just an arbitrary function. And as I said an hour ago, the predominant approach in imaging is to then maximize this posterior probability, or density, sorry, or equivalently to minimize the cost function phi. And if we're in this setting where phi is convex, then usually we can do this very efficiently, even in very high dimensions, by using state-of-the-art convex optimization algorithms. So this is the first class of problems that I'll introduce. Tomorrow I'll talk about problems that are significantly more difficult. But because many of you are already familiar with this class, and this is an interesting class, I'll start with this. So again, remember, for instance, in this problem, rate interferometry, I have a model that might look like this, a data fidelity term, a prior that involves, I don't know, L1 norm of a wavelet representation, and I can go from here to here, but knowing the map estimator does not answer a lot of interesting questions that I might want to answer. So for instance, if these structures are here, how confident I am about their energy, what would happen if I used a different model. Okay, so just a quick recap. How do you compute this solution? How do you get X-map? Well, many of you are already familiar with this, but for completeness and because many of you might not be familiar with it, I'll explain. So let's say that you want to find the minimizer of that cost function. Usually what you would do is you would split the cost function in two terms. One term f and one term g. And the splitting is such that f is a nicely differentiable function. So that means it is Lipschitz differentiable. So that means it is not only differentiable, but the derivatives are not doing any crazy thing. They are changing quite smoothly. Whereas g is complicated in the sense that it involves a term that is not differentiable. And then this is a constraint on the parameter space, which is 0 if you satisfy the constraint and plus infinity if you don't. So that's, yeah, that's a problem. So standard vanilla optimization algorithms like gradient descent will not work because this term is not the kind of terms that gradient descent likes. You have to do something a bit different. So one of the easiest things you could do is to do a proximal gradient algorithm instead. So this is a bit like a gradient descent, but it involves a gradient and a prox operator. Now the prox operator is a cousin of the gradient that comes from a different branch of analysis. So computing a derivative or a gradient, that is something that we do quite naturally when we do differential calculus. The proximal operator is a bit of an analogous object, but from convex calculus, which is a different way of doing calculus that is particularly well suited to deal with convex functions. So what is this proximal operator doing? Well, what it's doing, if you have a function g, it is adding a penalty, quadratic penalty to g around the place where you want to compute the operator, and then computing the minimum of these two things. So how does this work? Well, let's say I have my function g, and it looks like this, and I want to evaluate the operator at some place. What I do is I put a quadratic term, and I minimize that. So if that quadratic term, which is controlled by some parameter lambda, is really strong, then I don't move at all, because the quadratic term does not let me move. So I stay where I am. The operator at x maps x to itself. And if the quadratic term was not there at all, because lambda goes to infinity and this vanishes, then what happens is that x is mapped to the minimum of g. So for lambda very large or very small, what happens is you either stay where you are or you go to the minimum. Now for values of lambda that are intermediate, what happens is you move a bit in the direction of the minimum, you don't quite get to the minimum, and you don't quite stay where you are. You're pushed a bit towards the minimum. So it's very similar to doing the negative of the gradient. But it is a bit different, and it works with functions that are not differentiable. And this is well defined if g is convex. It can also be defined in other conditions, so you can relax that a bit, but for today we'll assume g is convex and lower semi-continuous. So in that case, you have two ways of minimizing. So when you do a gradient step with so shouldn't there be a minus LF? Anyway, I always make these mistakes, but it doesn't matter. In one case, you follow the gradient, and in the other case, you follow the prox. And with that iterative scheme, you're going for solutions that make f decrease and g decrease, and we can show that that kind of object will converge to the minimizer of your cost function, which is the sum of g and f. And it converges with a good rate of 1 over m. And if we do some modifications, instead of using constant steps, we use steps that are chosen in a way that is a bit more clever. Then in some cases we can accelerate this, and it converges superlinearly. So the key message here is that there's ways of minimizing this cost function, despite the fact that this is not differentiable, and that a key ingredient is to use the gradient of the differentiable part, the Lipschitz differentiable part, and the prox operator of the non-differentiable part. And that the prox operator is in many ways behaving like a gradient mapping, albeit some mathematical technical differences that are very relevant, but that are morally not that important. You're basically using a different way of finding a direction to minimize your function. And another algorithm that people use a lot is ADMM, so this the method of multipliers. And here we use the prox of both functions f and g. This is another example of an iterative algorithm where you just use prox operators to minimize the sum of f plus g. So what we have at the moment is a wide range of models where we have designed the model such that we have convexity, and a wide range of algorithms to minimize cost functions for those models. And that function that we minimize usually has a prox operator that we know how to compute or to approximate sufficiently well. Why? Because for a long time we've been trying to compute these map estimators, and this is the recipe that we follow. So most people who are working on a problem, if they have been working on that for a while, they have a model that works okay, and they have an algorithm that works okay, and usually the main ingredient of the algorithm is the gradient of the differentiable part and the prox of the non-differentiable part, or the prox of both parts if they have those proxies. However, at this stage, we compute X-map very efficiently, but there's a number of things that we can't do. So one is we can't really say much about the uncertainty around the solution. Then this works fine when G and F are perfectly known, but if I mess with you by saying that I don't know the noise level or the regularization parameter or the exact values of the linear operator A, then things very quickly become a lot more difficult and we start to struggle. So we struggle with models that are unknown or partially unknown. And then, as I explained a bit earlier, from a Bayesian point of view, it's not very clear why you should be computing X-map anyway. So, okay, it's the value that has highest density, but we saw that in Bayesian inference, we don't just postulate an estimator, we think of a cost function that is a good way of comparing two solutions, and then we go for the estimator that is optimal in this sense by using Bayesian decision theory, and it's not very clear what we are doing by computing the maximum of the loss function. What is the decision that you're making there? So let's adopt a different strategy. Let's, instead of trying to minimize the cost function, let's try to compute expectations and probabilities so that we can apply Bayesian decision theory and solve the problems in which any Bayesian statistician would solve them. So just compute the posterior mean, or compute a hypothesis test, or a credible interval, or compare two models, do any of these things. So what we need to do is compute expectations of some function h. This is not the regularizer, it's just some function h, given y. So h, if h is equal to x, then this is the posterior mean. If h is x squared, then this will relate to the covariance of x. If h is some indicator, this will be the probability of x belonging to the set defined by the indicator. So if we know how to compute this, then we can do almost all of the things that we wanted to do. The problem is I don't know how to compute these expectations, so what I'm going to do is Monte Carlo integration. I'm going to get a lot of samples, capital X, distributed according to my posterior distribution, which is the distribution against which I want to compute the expectation. And then I'm going to approximate the expectations by using this Monte Carlo estimator. So just the average of h evaluated at each one of those samples. Now, why are we computing expectations in this way? Why are we integrating numerically in this way? Well, because this is a way of computing integrals that is independent of dimension. So the error that I have here is independent of dimension. Whereas if I was discretizing my function on a grid and doing rectangles or trapezoids or anything like that, that error would grow with dimension very quickly, exponentially, and it wouldn't work in high dimensions. So I'm going to use this strategy. I also particularly like working with this because since x is a random variable, I feel that representing it through a population of samples is a natural way to represent a random variable. Right? If you have something that is a random variable, a sample is like a natural representation. And then it's also nice that under some basic conditions, I can put error bounds on this estimate because this is an average of many random variables, and if you've done a bit of statistics or probability, you might remember that there is a central limit theorem that acts on averages. So this will converge to its expectation, which is this, plus minus some estimation error that will decrease as capital M increases. So that's our strategy. Whenever we need to compute an expectation or a probability, all we have to do is generate m samples from x, m sufficiently large, and then do an average, and that's it. We've computed our probability or our expectation or quantiles or whatever you need to know. Now, how do you generate those samples? Well, if the model was low dimensional, that would generally be easy. But in high dimensional settings, it's really difficult to generate samples that come from P of x given y. And one strategy that is very general, and that's one of the reasons why I like it, is that you can construct a Markov chain that will iteratively generate those samples. by dancing around the parameter space. So what you need to specify is a Markov kernel, and a Markov kernel is just a rule for generating a random variable. Once you know the state of the random variable at a certain iteration. So let's say I'm at iteration m, I know the value of x at iteration m. Now I want to transition to a new stage m+1, and I'm going to do a transition that is not deterministic. I'm randomly going to choose to jump somewhere else, and I'm going to do that jump according to some rule, and that rule is the Markov kernel. So the Markov kernel, all it needs to know is where you're standing currently, and it specifies a distribution for where you'll land next, and you'll realize that transition. You will choose somewhere, you'll land somewhere, and you're going to jump around space that way. So I'm standing here, and I'll jump here, and then I'll jump there, and then I'll come back. And I'm going to choose these jumps such that after a while, I forget where I started. And I reach an equilibrium state where I'm dancing around the room, and the probability that I'm anywhere specifically in the parameter space is precisely p of x given y. So I'm going to construct this chain, this sequence of values, such that I start somewhere, and then I randomly decide where to move next at each iteration. And after a while, I forget where I started, and I reach equilibrium. And the equilibrium is precisely, by construction, the distribution I need to sample from. So once I've reached equilibrium, if I now start recording the values of x, what I get are precisely samples from p of x given y. Then I do my average, and I have my estimator. So this is fine, but constructing this kind of Markov kernel that reaches stationarity at p of x given y in high dimensions is difficult. If you follow any naive strategy from a standard computational stats textbook, it will not work, because these strategies don't scale well with dimension, and the people who do this, they don't usually have images in mind, they have other kinds of data sets, and this does not scale to dimension 1,000 or 1,000,000, unless you're very careful about how you do it. And one way of doing it that scales to high dimensions is to inspire yourself from some kind of physical stochastic process that by construction naturally converges to p of x given y, even if the dimension is really high. So one such process is the Langevin diffusion process, defined by this stochastic differential equation. So if you're not familiar with stochastic differential equations, today is not the day in which you will learn about them. But let's just say that it's an equation that acts on random variables. So at time t, x has a certain distribution, and at time t plus delta t, that distribution is changing a bit. And the way in which it changes is defined in this way. So the random variable xt, when I look at the differential, this difference is determined by the gradient of log p at the place where xt is standing at time t, plus a Brownian motion. So here I'm integrating against the Brownian motion. So it's an equation that is not deterministic, it's acting on random variables, and it's driven by a stochastic process. And I could rewrite this and make the stochastic process disappear and just say that I'm acting on the distribution of x, because here I write it with x explicitly there and not explicitly the distribution of x at time t. I write it in this way. It's more convenient for what comes, but essentially what you need to understand is that xt is a random variable, but it depends on time. It evolves in time, and as time goes on, its distribution changes, and this specific equation leads to a situation where xt, as t goes to infinity, converges to p of x given y. Now, all I have to do is solve xt, let t be large, then evaluate at different times t, and this will give me my samples. The problem is that I can't do that because I can't solve that stochastic differential equation exactly. So what I need to do, like most people do when they deal with differential equations of this form, is to discretize it and compute a discrete approximation where time is not continuous, it's discrete, but if I'm a bit careful about how I do it, then it's a good approximation that becomes even better when I let the time discretization step go to 0. The easiest way of discretizing this is to use an Euler approximation. And when you do it for a stochastic differential equation, that's called an Euler-Maruyama approximation. And all you do is you replace this differential by sort of like xm plus 1 minus xm divided by delta. And what you get is this kind of recursive or iterative scheme. At time m, x has value xm. Then you add a gradient step, a bit as if you were doing a gradient descent or gradient ascent. And then you add a Gaussian perturbation. So at each iteration, what you need to do is draw a Gaussian random variable and compute this update rule. And then you get a new position xm plus 1, which is essentially a Gaussian perturbation to this deterministic step. So you're standing here, the gradient thinks that I'm standing here, the maximum is there, the gradient is going to push me a bit towards the maximum, and then there will be a Gaussian jump around that, and then again towards the maximum, and then another Gaussian jump around that. So I'm going to dance around space. I'll never stick in one point, I'll be dancing around all the time. But it turns out that I'll be dancing with a distribution that is very close to P of x given y. Why it is not exactly P of x given y? Well, because I'm not doing this, I'm doing that. This is a discrete approximation. But we now have theory, mainly thanks to a few French people, Eric Mullin, Alain Dormus, Arnaque Dalalien, and some other people, Pages. And they showed that this stays very close to that in various different ways of measuring distances and closeness, like Wasserstein and TV and Kullback-Leiber and different things. They also showed that this is remarkably efficient when dimension is high, provided that P of x given y is sufficiently regular. So if this object here, this gradient is Lipschitz, then things behave quite well. Provided you have convexity and hopefully strong convexity, then things are really good. In the stats community for a long time, we didn't have those theoretical results. And so we used a different trick, which is a standard stats trick, which is called the Metropolis Hastings correction. And this is a correction for taking any way of constructing a Markov chain to change its stationary distribution to make sure it's exactly what we want. So the way it works is, let's say you are using this update rule, which we call an adjusted Langevin algorithm, so ULA. Well, what you do is, once you have proposed to generate your next step with ULA, then you apply an accept-reject procedure. You compute some probability that is defined here, which doesn't matter, it's something you can compute. And then with this probability, so you draw a random variable from 0 to 1. If it's smaller than this value, you accept, otherwise you reject. So with this probability, you accept this proposition for your next move. And with 1 minus this probability, you reject it, you stay where you are. So it turns out that you can take pretty much any way of dancing across space, and if you add that extra value, this changes your stationary distribution from what was the original stationary distribution to exactly P of x given y. So either if you don't have theory for your method to show convergence, or if you don't have the exact distribution and you're really worried about this error, this bias, because you're not targeting exactly P of x and y, then you can add this correction and it will automatically fix your error, and asymptotically you will target the exact thing you wanted to target. And I don't want to talk too much about this probability, but it's something we can compute and the algorithm works. Yeah?
On the imaging applications that you have in mind, the acceptance rate is very close to 0? Or?
No, the acceptance rate is something you can control with delta. So if you, in this particular example, so if you used a generic way of proposing your moves, then it would be, in imaging, it would be rubbish. But because your original starting point is a diffusion that targets exactly what you want, and you know that for delta small enough, you are getting very close to that exact thing, here, if I make delta small enough, then the effect of the correction becomes almost negligible. And your acceptance rate is very high. You're constantly proposing moves that the algorithm likes, and it's always accepting. What happens is that in that case, you're not moving across space very quickly, because each time you do an iteration, there's only a very small time increment. So you were here, and then you're here, and then you're here, and then you're here, and it takes you a very long time to actually do anything. On the other hand, if you take long steps, then you do jump far, but very often the algorithm says, no, go back to where you were. So you stay stuck. So in both cases, you get algorithms that move very slowly, and they don't converge to the solution in an amount of time that you find satisfactory. And luckily, mainly thanks to people at Warwick University, we know what is the exact value of delta we should be choosing. So they have done theory, and under very general conditions, for this algorithm, you should be aiming for an acceptance rate that is close to, let's say, 60% or 50%. And if you have delta such that the probability of accepting or rejecting a move is around this value, then your chain has an efficiency as measured in a statistical sense that is optimal. This is as good as it gets. And it turns out that a big advantage of this kind of Markov chain algorithm as opposed to an optimization algorithm is that Markov chain algorithms calibrate their parameters on their own. So in optimization, you usually have some parameters you need to choose, and if you choose them poorly, it can work poorly. So you can take a long time to converge to solutions. So in, I don't know, ADMM, there is a balance to have between some residuals. There's situations where things go wrong. MCMC algorithms avoid that by self-calibrating their parameters. So what you can do is add this update rule, and then your algorithm acts like a stochastic optimization scheme. At each iteration, you get a value of ρ, and this value of ρ is like a realization of a random variable for ρ, and what you want is to make the expectation of ρ equal to 0.6. That's what the theory says. So you compute ρ against 0.6, and then if ρ is too large, then you make delta larger by adding this. And if it's too small, you make delta smaller by subtracting that difference. And you can show that this scheme with this adaptation loop will not only converge to the distribution that you want, but in fact, delta will stabilize at the value that gives you the acceptance rate the theory says is optimal. So when you run MCMC algorithms, they are not as fast as optimization algorithms, but usually under some basic regularity assumptions, they tune themselves and then they run. So you run it, you go on holidays, and when you come back, you have your answer. No, I'm kidding. But yeah, when I did my PhD, some of the algorithms that I was working on were really slow. And that's one of the reasons why I started working on new algorithms, because it was just frustrating to have algorithms that were so slow. So we weren't doing anything like this, like Langevin. We were just sort of like random walking across space and deciding to accept and reject. So it was rubbish. Yes?
Can you please comment on the right part of the acceptance probability? This is not posterior.
No. So what you're doing is the ratio of the posterior where you propose and where you currently are, and you're compensating that by the ratio of the transition kernels. So the idea is your proposal mechanism is going to push you to some part of the parameter space. So you want to compensate for that. So you compensate that by doing a ratio that is the inverse of that. Now, if you're standing at xm and moving from xm to x star, it's very likely you'll penalize that. And the way in which you'll penalize that is with this ratio. So this guarantees that the whole thing converges to this one and not to that, because otherwise you would always be moving according to this transition kernel. So what happens in imaging? Well, one of the reasons why we hadn't been using this in imaging is that imaging models don't satisfy the regularity assumptions that you need to use the Langevin dynamics. So the Langevin dynamics work really well when everything is smooth, when you have Lipschitz differentiable gradients. If you don't, then one of the things that can happen is that this guy blows up. It becomes explosive. So you can't use it. And if you add the Metropolis-Hastings correction, it never converges. So you can show that if you start at stationarity, you will stay at stationarity because this guarantees that this is the invariant distribution, but you never get to stationarity. So it doesn't work. So for instance, if you're dealing with models that look like this, a smooth term that is Lipschitz differentiable, and then a nasty term G that has the non-differentiable parts, you can't use ULA. Or MALA. MALA is the Metropolis adjusted version of ULA. And yeah, and that's, I mean, that and the fact that the stats community and the imaging community don't talk as much to each other as they should is mainly the reason why we were not using those methods in imaging. And the idea that I'm going to present now is very simple. What I want to do is to regularize P of x given y, such that by construction I can do Langevin on it. By construction I can also do other things like Hamiltonian, Monte Carlo, but there is no originality there. I'll skip all of that. I'll focus on this algorithm. But let's just say that all the algorithms that work really well in high dimensions, they need geometry information that usually comes in the shape of a gradient, and that if the gradient is not Lipschitz differentiable, then the algorithm blows up. And what I'm going to talk about now is a general way of regularizing your model such that it never blows up and it converges to what you need. And there's many ways of doing it, but the one that I'm going to present is interesting because A, it is very general, and B, we have theory to show that it's safe. So what I'm going to do is I'm going to take this term G that is unpleasant, and I'm going to replace it by an approximation called G lambda. And G lambda is what people in convex calculus call the Moro-Yoshida envelope of G. So it's basically G plus this quadratic approximation, and then at this point I compute the infimum of this. So it's very similar to the prox operator in sense of the expression, but the prox operator was a mapping that would take x and output a new value in the parameter space. This is turning x into a scalar value. And it is acting as a smoothing operation on G. So let's say I was smoothing G with, in the standard way of smoothing with sort of like differential calculus. What I would do is I have G. G has some parts that are not sufficiently smooth. Then I would, for instance, do the convolution with a Gaussian kernel. That would filter out any unpleasant discontinuities in G or places where it moves too quickly. So you're all familiar with this. We do it in signal processing and right at the beginning. You sort of like filter your signal with a Gaussian kernel. This is doing the exact same thing. It's just the convolution is a bit different. Instead of being a linear convolution where you integrate against the Gaussian kernel, you can see this as taking an infimum against the product of exponential of G and exponential of minus this, which you can also write this way. So you can, what you're essentially doing is you're smoothing out discontinuities, but instead of using the standard convolution operator, you're using an inf convolution, which is the way in which convex calculus prefers to do convolutions. And we are choosing this strategy because it will have some beneficial properties, and lambda controls how much I approximate. So lambda, if lambda is very small, then G of lambda will be very close to the original G, and if lambda is very large, G of lambda will become a bit different from G, so I will have approximation error, but I'll have something that is a lot smoother and a lot easier to explore with a Markov chain. So what are the properties that we know about this? Well, we know really a lot of things. Here I'm doing a summary of the most relevant properties. So what we know is that P of lambda, the modified posterior, is a proper posterior density. So it's fine to work with that. We know that if the original model was log-concave, so if we had something that was convex to compute the map estimator, what we get is still log-concave, so it's still fine. And then we know, crucially, that by construction, regardless of exactly the shape of f and g, as long as one is Lipschitz differentiable and the other one is replaced by the Moreau-Yorshid envelope, the approximation is always continuously differentiable, and it's Lipschitz gradient. And the gradient has this expression here, where all you need to know to compute it is the gradient of f and the prox operator of g. And we know the Lipschitz constant of this. So if you have an algorithm to compute the map estimator, and you have in your code the gradient of f and the prox of g, then you can very quickly change that code to now have the gradient of log p lambda, sorry. And how bad is this approximation? Well, it's not that bad. If you choose lambda small, you converge to p. So you can show in different ways. Here it's in TV norm, which is a way of measuring errors in terms of worst case scenario if you compute a probability with respect to p instead of p lambda. We can show that there is no estimation error when lambda goes to 0. And for finite lambda, if we're in the case where g is Lipschitz, so for instance the L1 norm, then I can bound explicitly the distance between p lambda and p in terms of lambda. So I have very good control of my approximation. I have turned a problem that is not Lipschitz differentiable and therefore beyond the scope of efficient Markov chain Monte Carlo methods into a problem that is sufficiently regular to do efficient sampling, and I will pay the price in terms of approximation error. My inferences will not be exact, they will have a bias, but I have explicit control of that approximation. So it's not blowing up, I'm not getting rubbish. I'm just having a bit of bias. And if you want less bias, then choose a smaller lambda and you'll pay the price with a worse Lipschitz constant. The worse Lipschitz constant will mean that your algorithm will be a bit slower. So how does this look in practice? So let's see, here we have 4 examples of models in one dimension that are not Lipschitz differentiable. The first one, the Laplace distribution that has an absolute value, is not differentiable here around 0. And what the model will do is it will make it Lipschitz differentiable, so this change cannot be faster than a quadratic function. What it's doing is it's changing this into a quadratic change. And if lambda is very small, then the approximation is not too bad, and as lambda becomes larger, you are making a coarser approximation, but this also has a Lipschitz constant that is much better for your numerical algorithm. X to the power of 4 is also not Lipschitz differentiable, because x4 is a change that is much faster than x squared. So what is happening is that in the tails, I am replacing the tails that are really fast with slightly slower tails that are quadratic. And again, if lambda is small, my approximation is quite good. And this is an interesting case, the uniform distribution, because the uniform distribution, if you think of the log gradient, it is 0 everywhere, or so if I go to minus log g and I look at the gradient, here it is 0, here it is plus infinity, and it is not defined in the 2 discontinuities. So this is something where if you wanted to follow a gradient, your algorithm would not work at all. The gradient would either be 0 or not defined. And what we get is an approximation that is very close to flat in the uniform region and then has Gaussian tails. And I can make the Gaussian tails as small as I want by reducing lambda, and I pay the price with a worse Lipschitz constant. So once I have this, what I can do is define a new Langevin diffusion process, so like an auxiliary diffusion, that is not targeting P that I wanted, it's targeting P of lambda. But because P of lambda can be made arbitrarily close to P, this auxiliary process can be made arbitrarily close to the original Langevin diffusion I wanted to target. So I'll do that. Now I'm targeting P of lambda, and I'll discretize this with an Euler-Maruyama discretization, and I get this scheme, where instead of expressing the gradient of G lambda in this way, I have used the prox. So now I have a scheme that has gradient of f and prox of G. But if you know how to do something like forward-backward splitting or proximal gradient or any convex optimization algorithm that uses these 2 ingredients, it should take you 2 minutes to change your optimization scheme into a scheme that will draw samples from X instead of converging to the minimum. So that's what we do. And there's different ways of refining this algorithm, but they're not particularly interesting to discuss, so I'll skip them. But you can, if you start reading about this, you'll find different refinements. Okay, so what do we know about this algorithm? We know quite a few things by now. And one of the things we know is that if you generate a Markov chain with this algorithm, and you run m iterations, so let's say, I don't know, you have your computational budget that allows you to run 10,000 iterations of this algorithm, then we can bound the error that you make by doing an estimation with the distribution of those 10,000 samples instead of using the true p. We can bound it explicitly. It depends on your lambda and your epsilon basically tells you what's the number of iterations you need. So for any number of iterations, I can find an epsilon, or for any epsilon, I can find a minimum number of iterations, such that at the end, your error is smaller than this. So what you have is a situation where if you can afford a certain number of iterations, you could bound the error, or if you are targeting a specific epsilon, which so far I've never found anyone who wants to target a specific epsilon tells me I need an error of, I don't know, like 1%. But if that was the case, you could, and then I would tell you you need, I don't know, 1,000,000 iterations, and that's the way it goes. What's more interesting is that by looking at the number of iterations that I need to achieve epsilon, and letting the dimension increase, I can know the complexity of my algorithm. So how is this number of iterations growing as the dimension increases? If it grows as, I don't know, exponential of d, then I'm in trouble, because when d is large, this algorithm will never achieve epsilon. And for this algorithm, we know that it converges with rate d log d when the problem is strongly convex, and otherwise it is polynomial. And at the beginning, it was something like d to the power of 7, and then it was d to the power of 5, and I think the latest results by Alain Dormus, maybe Valentin remembers, I don't know. I think the last ones are d cube. Empirically, we observe results that are much better than d cube, but there is maybe some pathological case, and it turns out that d cube is the worst case. But what we observe in practice is things that are a bit closer to this. Usually, if your problem is not strongly convex, it is also not strictly convex in all dimensions. So what you might have is one dimension where things don't scale very well, but other dimensions where it does. So it's not too bad. So we have a scheme that has a complexity that is not orders of magnitude different from an optimization scheme. Algorithmically, it is similar to an optimization scheme, and we can use it to do Monte Carlo inference, Monte Carlo integration, and Bayesian inference instead of optimization. So if I run that for my simple vanilla examples, I get the histogram of the samples for a Laplace distribution, or the histogram of samples for x to the power 4, or an approximation of the uniform. So the algorithm is doing more or less what we expected it would do. If I go for a smaller lambda, then I'll get a better approximation, but I'll need more samples because those samples will look very similar to each other. I'll need many iterations to get two samples that are really original and bringing new information. Okay, so skipping an obscene amount of other methods and refinements and ideas of how to do Bayesian computation in imaging, but there are two surveys that I wrote with colleagues recently that you can consult, and they cover a big part of what has been done that is relevant to imaging up to 2-3 years ago. The plan is to write a new one later this year. Okay, so once we have an algorithm, what can we do with it? Well, we can revisit all of my elephants from an hour ago. So let's say I want to do uncertainty quantification. Instead of computing an estimate for x, I want to get a set of solutions, C alpha star, that has lots of solutions, an infinite number of solutions, with high probability. So some good candidates of what the true image looks like. So if I do that, for instance, in the one of the radio interferometry problems, this is the estimate that you do if you just do like least squares, penalized least squares. So it's rubbish. It's what we call the dirty image. And by computing the map estimate, we were getting here, and that was good. We're very pleased about that. And by we, I mean the community. I didn't come up with a way of computing a map estimator. And what we have now is, in addition, we have credible intervals. So what we can do is, for instance, say what parts of the image we really trust and what parts we don't trust, and by how much. So what we do is, we can do this at different scales. We can start at the scale of a pixel and then move to larger scales, groups of pixels, and say, well, if you are looking at a structure of size, I don't know, 10 by 10 here, for instance, in this part of the image, then the confidence interval would be this big. And what we're displaying there is how large the confidence interval is. So this is a good way of visualizing areas of the image that you really trust and areas that you don't trust. And it also has some other applications. For instance, in many of these radio interferometry problems, the operator A they use is not known that well, but they have a good approximation. What they do is they solve the problem with their guess, and then they take parts of the image that they really trust. Usually they were just choosing parts with high energy, and then they re-estimate the operator based on those high energy pixels, and they resolve the problem. And what you can see here is that by computing the credible intervals, you automatically know what all the regions that you should trust, and it turns out that it coincides with what they had heuristically found was a good way of calibrating the model. You can also compute other estimators. So you might wonder, maybe the map estimator is not the only, it's not the best option. We could compute something else. So here I'm computing the posterior mean with the algorithm and with the algorithm that has the Metropolis Hastings correction. We see that the estimates are quite good. There are some minor differences in the background, but otherwise the biased estimate is really good. So in this scenario, we see no reason at all to use Metropolis Hastings corrections. They make the algorithm slower. And if we compare the posterior mean with the map, we see that we're getting something that is also very similar. So I wouldn't necessarily compute this estimator if you already have a map estimator you can do by optimization. And this is also interesting because this is a model that has this, sorry, so I'm not representing the model. This is the model that had this L1 term on the wavelet coefficients, and there's a lot of people that debate about whether when you have a prior that looks like this, that has an L1 term, whether the Bayesian approximation is valid or not. In some communities, they attacked a lot mathematicians that didn't want to use the Bayesian interpretation. They were going like, what you're doing is just putting a Laplace prior, and it's not a good idea. Mathematicians sometimes do the opposite and go like, this is not a Bayesian model. This is just, you're regularizing with a L1 norm, and it's not a Bayesian model, because if you draw samples from the prior, if you draw samples from this, they don't look at all like something that has, like a sparse set of coefficients. And there's a lot of papers with interesting mathematical results about that. But until now, we had very few actual examples of what estimates of the image look like if you are doing Bayesian inference and you're not computing the map estimator, which has this plurality of interpretations. One of the things I'm doing now is computing estimators for different problems and showing that in many cases, the estimators that you get are very similar. So the Bayesian model is not doing anything silly. The mass is concentrating where you want. And in some cases, this is shown theoretically as well. Okay, so some things you can do with the algorithm. Other things are to do model comparison and model averaging. So let's say I have k different models to solve my problem, and I don't have ground truth, so I can't choose one specific model. I need to entertain all these models and select one based on the data. So as I said an hour ago, you can compare them based on their probabilities. Now, how do you actually compute these probabilities? It's tough. It's a very high dimensional integral. So there is an estimator you can use that I'll show in a minute. So first, I define 4 different models. So I've generated some synthetic data using an operator A star that I know and added some Gaussian noise. And then the 2 models A1 and A3 have the correct operator A. And then the two models A2 and A4 have an operator that is just a bit different. In one case, I had a blur of size 5 by 5, and in the other case, I extended the blur to 6 by 6. It's a bit different, but it's not that different. And it's because I want to test if I can distinguish things that are really similar. Of course, things that are very different are easier to distinguish. And then I have two candidates for my prior. One is a TV prior that promotes piecewise constant solutions, and the other one is a prior that promotes sparsity on a wavelet frame. And here it's a lot more difficult to argue that one model is better than the other one, unless you have ground truth, because one will produce solutions that agree with TV, and the other one will produce solutions that agree with wavelet sparsity, and which one is a better solution or closer to the truth is not an easy question to answer unless you formulate it in this way. So what I'm going to do is I'm going to run one Markov chain for each one of my models using our algorithm, and then I'm going to compute this estimator of the probability of the data given the model, and from this I can infer the probabilities of the models. And I will not explain the estimator in detail, it's just an estimator you can use. You have to be careful about how you use it, but we found that it works okay. And what we get is that the two models that have the true blur, the true linear operator, are scored as good models, and the two others are scored as really bad models. And between the two, the data prefers the total variation regularization as opposed to the wavelet regularization by a factor of 2. So it's not a dramatic factor, but it's, yeah. So clearly, just from the blurred image, we can decide if these two candidates for blur that we have are equally good, or if there's one that's better than the other one. And we can also decide if one regularizer is a bit better than the other one or not. It doesn't mean we're going to get it right, but it provides a principal way of making a decision. And if we run this with the Metropolis Hastings correction to have something exact, the approximation error will be less than 1%, so it's not a big error. So this is just an illustration of how much you pay for having an exact algorithm. So if you do a Metropolis Hastings correction instead of having the standard algorithm, it takes you like 100 times, it's 100 times longer to converge to stationarity. And once you're at stationarity, the time it takes for you to forget, let's say you're at sample 10, the number of iterations you need to make to get a fresh new sample also grows a lot. So whereas in one case, in roughly 400 iterations, you have completely forgotten the value of your previous iteration. With the other one, it takes you thousands of iterations to get there. So you would have to run it a lot longer. And I'll conclude my talk, probably the next 20 minutes I'll need for this, with the case of unknown regularization parameters. So if you have not been focusing until now is a good time to wake up, because this is probably one of my favorite things from the last couple of years from what we've done. Anna is working a lot on this. Valentin is also working on this. And it provides a general strategy for setting regularization parameters that is working quite well in practice, and that is mathematically very cute because it combines lots of things that are fun. So let's say I have a class of models indexed by a regularization parameter that I don't know. Each time you fix your regularization parameter, you have a valid cost function, a valid statistical model. But you don't know which one to use, so you have a class of models indexed by this parameter. And let's assume for today that the shape of my prior is like this. I have exponential of minus theta, some penalty function. And I'm in the case where everyone is convex and nice, and if I had the value of theta, I would be able to solve this efficiently, but I don't. So what I have to do is somehow work with this prior to find a good value of theta. But working with this prior will turn out to be difficult because the normalizing constant C of theta, which in optimization we always ignore because it's not a function of x, well, it is a function of theta. So when you need to find theta, you can't ignore it anymore. So we need to find out what's that value. And this value is a complicated integral. The integral of this exponential function in a very high dimensional space. So this is very difficult to estimate. If we had theta, life would be beautiful because this is a convex optimization problem. And I would just apply proximal gradient or anything of that flavor, and I would get my estimate. Something like this. But when theta is unknown, then the problem becomes significantly more difficult because, well, it's not very clear what to do. So we're going to pursue the Bayesian way, one of the two ways that we described earlier. Now we're going to find one specific value of theta to solve the problem, and tomorrow I'm going to talk about using all values of theta simultaneously. So what value of theta are we going to choose? Well, we're doing what people call empirical Bayesian inference, and that basically means we're going to find the best value of theta in the sense of maximum likelihood estimation. So, as I briefly commented, the likelihood function is a very good function to choose things, provided that it points to a very specific solution. So if theta was of dimension larger than y, that would not be a good idea. But here, y is, I don't know, a set of pixels or measurements. It's quite large. It's at least, I don't know, 1,000, 10,000. And theta is dimension 1 or 2. I mean, how many regularization parameters do you want to have if you don't even know their value? So let's say I have 1 or 2. What I want to do is find the maximum of this. And this maximum will usually be very close to the true value of theta, if you can imagine something like a true value for a regularization parameter. But in any case, it will be the value that maximizes this. The problem is that this function is not something you know. You know it's the integral of the joint of x and y when you remove x. But maximizing this innocent optimization problem in dimension 2, it is extremely difficult because this function you want to maximize is untractable. So you can't just take the gradient or the logarithm and the gradient because this is not something you know. And it is untractable at many levels because it is untractable because of this integral, and inside what's hiding is this other integral that is also untractable. So it's full of untractable elements. And what we're going to do is we're going to construct a stochastic gradient algorithm that Anna briefly explained yesterday in her poster. And we are basically going to combine gradient steps with Monte Carlo steps in a very careful way such that our stochastic sequence of values of theta converges to the maximizer of this optimization problem that would be otherwise completely untractable. So people in machine learning are very familiar to stochastic optimization problems, but their stochastic problems are different. They assume that, I know, they have a lot of data, and if they had to compute the gradient with all this data, it would be too expensive, so they subsample the data. Here it's a different animal. What I have here is a very high dimensional integral, and I can't just subsample elements of my model. That's not the issue. The issue is that I have an integral over all possible images, so what I will have to do is draw examples of images and then do stochastic optimization in the way a machine learning person would do it. So how do we do that? Well, let's first suppose that I could compute gradients. So one of the things I could do is use a gradient algorithm. So that comes from this fixed point equation. I want theta to live in capital theta, and I know that if theta verifies this fixed point equation, then it is my maximizer. So if this term, this gradient term here was tractable, then I could just do this sequence and iteratively update the value of theta until I get to the right value of theta, the maximizer. It would stabilize at the maximizer. This is a problem in dimension 1 or 2. It should, if this is sufficiently regular, I should get a solution pretty fast. In fact, in most cases, this is p of log p is almost quadratic, so you converge very quickly to the minimum in dimension 1. The problem, as I said, is this operation is untractable because there are two integrals that I can't compute. So what we're going to do is first rewrite this in a way that allows bringing in Monte Carlo estimation. So I need to write this as an expectation or a probability or something like that. So I'm going to write it as an expectation. The first thing that I do is I re-express this as this expectation. by using something called Fisher's identity. So it turns out that I have some gradients and some integrals, and they can commute, so I can rewrite things. I can rewrite the derivative of this thing that has an integral as the integral of that thing that has a derivative. And this expectation is an integral that I know how to compute by Monte Carlo estimation. If I have samples of x given y and theta, I can compute this gradient. Now I have my second intractable term, c of theta, which is also intractable because it also has an integral. But it turns out that there is this identity from the 50s that was a bit undetected that says that the log gradient of c of theta is also the expectation of phi. And this is the identity that I used an hour ago when I was telling you that when you set this kind of prior and you set a value of theta, what you're setting is this expectation. And it turns out the expectation depends on the gradient. And now this is useful in the other sense, not because I want to set the expectation, but because I want to replace the gradient by an expectation. So what I obtain is that the gradient of log p of y given theta, which is intractable, is in fact the difference of these two expectations, which I could compute if I had samples of x from the prior and from the posterior. So what I need are two Monte Carlo schemes to get these samples. So I can rewrite my fixed point equation as this fixed point equation that still has integrals that are intractable inside the expectations, but unlike the previous expression, provides a clear path towards getting estimates of these expectations. So what we're going to do is this algorithm that I really like because it has Markov kernels and a stochastic optimization step, all built in the same algorithm. So what you do is you draw a sample of x from the posterior, but it's not exactly from the posterior. It just comes from a Markov kernel that will asymptotically converge to the posterior. And you draw a sample from the prior, again not exactly, but just with a kernel that will iteratively get you closer and closer to the prior. And you update theta with this scheme, and by putting the random variable u here, you are getting something that is an estimate of the expectation. And here you have an estimate of the expectation with respect to the posterior. And these estimates are not the actual expectations. They behave as random variables whose expectation is the right expectation. So each time you do an iteration, you make an error. But as you iterate, these errors average out because sometimes they're positive and sometimes they're negative. And if your estimates are unbiased or have a bias that is not too bad, then the fact that you're multiplying by a term delta t that will have to make go to 0 makes this scheme converge to the truth. So you have now an object that involves two random variables and a deterministic parameter theta, and you're doing an update that looks like two Monte Carlo steps, two Monte Carlo transition kernels, and one deterministic update for theta. And it turns out that this strange object converges to what we need. Theta converges to theta hat, and x and u converge to the posterior and the prior indexed by theta hat. So this whole thing converges to a space that is a product of two distributions or two random variables and the space where theta lives, capital theta. And again, the fact that this kind of scheme converges is mainly, we know this mainly thanks to 3 or 4 French probabilists. And now for the last scheme that I'll present now, it's Valentin, Alain, and Jormus that are working hard to show this. So when we want to generate the samples, in our case, we'll do proximal Markov chain Monte Carlo, so we'll do proximal Langevin, the unadjusted version because it's enough, and we'll end up with these update rules that are what I described half an hour ago, and then we'll do a gradient step here for theta, and we'll report as our estimate the average of all the thetas, and we know this average converges to theta hat approximately because I have an approximation error in the Langevin diffusion. I'm not using the continuous time, I'm using the discrete time, and I don't want to use a Metropolis Hastings correction because it slows things down unnecessarily. And this is the object that I find very beautiful, because you have two schemes. These two schemes are very close to optimization algorithms. In fact, the prox operators are solving an optimization problem. Simplified, but it's an optimization problem. So you're using something that looks a lot like an optimization scheme, but you're adding random variables to approximate a stochastic process, the Langevin diffusion. You have two Langevin diffusions that are coupled through theta, and then you put that into another optimization scheme. That's now a stochastic optimization scheme that is driven by Markov kernels, and this whole thing converges to what you need. So it has completely blurred the distinction between optimization and sampling. Now, this object is really a proper chimera of optimization and sampling. You can analyze this as an inhomogeneous Markov chain controlled by a feedback loop, or as a stochastic optimization algorithm driven by two Markov kernels. So how does it work? Well, it works really well. At least in the examples, most of the examples we've found. So again, this is the microscopy experiment I was explaining earlier. The goal is to do sparse deconvolution from this to this. And it was an interesting test case because here we know that these molecules are really sparse, so they have nothing to do with this. So it was a bit of a gamble to see if the model would identify a value of theta that it was good or not. And it does. It converges very quickly in just 100, 200 iterations. It gets very close to a value that gives a very good reconstruction. So in this case, we know the best reconstruction. We have ground truth. And it takes, in this example, it takes just a second on a laptop. It's very fast. It's usually not this fast. It's just this model is very easy to sample from. And here we have another example on the convolution of a boat image with a TV prior. And here, just for the sake of the presentation, I added a quadratic penalty term to make everything well defined. In practice, I think we ran the algorithm with alpha 0 and alpha really, really small, and it worked fine. In any case, we assume that alpha is fixed to some value, and what we want to estimate is theta. And so these experiments are thanks to Anna. And what we see is that in a couple of iterations, let's say 500, 1,000 iterations, theta converges to a value that is not too far from the optimal value that we're showing here, because we know with the ground truth, we know the original boat image. And if we look at the curve of MSE values, we see the optimal is somewhere here, and our estimate is just next to it. The green cross is another method that I'll explain tomorrow that I proposed a couple of years ago, where you use all values of theta simultaneously. And the red cross is sugar, which is a method that does a completely different non-Bayesian strategy. Jalal, Gabriel, and Deledal propose this. It usually works much better. In this example, it doesn't. And this is not a general reflection on the performance. There are some examples where it works better than ours and some examples where we do better. But of course, I was not going to start by showing you the example when they do better, because it's just, what would be the fun in that? And now what we found is, so this other approach works perfectly when you're in a denoising problem, and the more you go from denoising to something else, the more it can struggle. And in this case, we have, I think, 30 or 40 dBs, so there's not a lot of noise, but there is a lot of blur. And in that case, we do better. When there is a lot of noise and not so much blur, they do better. And then there's many cases where they do similarly. So here we have, for different noise levels and a strong blur in all cases, the performance of our method and this other method, which for me was the best method available. And what we see is that yeah, when there is more noise, then both methods do similarly to the oracle. Here we do a bit better because there's a lot of blur. If there was less blur, they would do better. The computing time is similar. When there's 30 dB, we stay very close to the oracle, and they improve, but not as much. And when there's 40 dB, again, the oracle is very good, and we are almost at the oracle. And this makes sense. I mean, maximum likelihood estimation is a really good way of estimating parameters. It would give provably optimal results when you have a lot of data and your model is perfect. Here, our model is not perfect, and that's the main problem, but it's still doing reasonably well. And yeah, so I think this algorithm has a lot of potential. We are, and by we I mean Anna, is doing a very exhaustive evaluation of this in different problems. Sometimes it works well, sometimes it doesn't. Sometimes you have to be careful. And yeah, so we'll report that on arXiv in a month or so. And I'll just conclude now by saying that so there's a lot of very good work in the imaging literature. There's a lot of new work that is very good in the imaging literature. But when we want to go beyond point estimation, then there are some big challenges there. And particularly, there's a lot of applications where we want to reconstruct an image to inform a decision or a conclusion. And then there is a bit of a gap in between the math we have and what we actually want to get out of the imaging problem as a solution. The Bayesian framework can support this paradigm shift, if you want to call it that way, but it has to be computationally more efficient. Otherwise, it will not be adopted, and it has not been adopted until now. So that's a big problem. And what I discussed is one way of accelerating Bayesian computation by using this Langevin diffusion processes. There's other processes you could use, and there's other strategies that are not using Markov chain Monte Carlo that you could use too. But this one seems to be quite general and work quite well in imaging problems. So I think it will be useful in the future. And what I also like is the fact that it draws a lot from variational approaches, and it brings the two communities closer together, which is also something I think is important. And what we'll do tomorrow is we'll describe some strategies that avoid using Markov chain Monte Carlo at all. And the key idea there will be to combine optimization not with stochastic methods, but with probability at a deeper, more theoretical level, and see if we can rewrite Bayesian inference problems as problems that can be at least partially solved by optimization. And yeah, that will be even faster. So I hope you'll find that interesting. Thank you, and we have 15 minutes for questions.
Okay, so other questions? So, yeah. So if yes, please wait for the microphone because we're recording this.
Okay, thanks very much, Marcelo, for this lecture. I was wondering, I have a few questions, maybe clarifying things also to the audience. So the first question I had in mind is, you presented a lot of stuff where the likelihood was quadratic, so its gradient itself is Lipschitz, and where the function has Maurer envelope, so it's convex, of course, it has Maurer envelope, which has gradient, which is Lipschitz. But the thing is that the likelihood has to be to have also gradient Lipschitz, which is Lipschitz. So typically, if you go beyond the Gaussian noise, for instance, if I have Poisson noise, then all this just blows up. So can you give us some insight on how to generalize all this to non-Euclidean metrics, for instance?
So I've not done work on non-Euclidean metrics for this, but the path we're pursuing to get beyond Gaussian models is, so we have a paper in preparation on specifically Poisson and non-Lipschitz likelihoods that are Poisson, binomial, things like that. And in that case, we're using either two prox operators, or we're doing the Moreau envelope of the Poisson likelihood and the Moreau envelope of the prior. We also looked at schemes where we just aim to compute the prox operator of the entire cost function, and we do that sub-iteratively. And in some cases, it is a good path. So if you have, I don't know, let's say an ADMM algorithm or prooimal dual to compute the map estimator. Then computing the prox of the whole function is that same problem plus a quadratic penalty term. And so what we do is we solve that problem at each iteration. But because the previous iteration provides a very good initial condition, you are warm starting your algorithm, and it works quite well. The convergence analysis is tricky because you never actually solve completely the optimization problem, so you have an additional source of error. But numerically, we observe good results. But there's many other directions to address that problem we haven't pursued yet.
My second question, so you mentioned that many people argue in the Bayesian communities that they can handle, even if they don't have log-concave distributions. What happens if you don't have log-concave distributions from the theoretical point of view, but also from the computational point of view? So,
well, it really depends on what kind of non-convex model you have. Tomorrow I'll talk about very wild non-convex models that have that sort of like involve functions that are heavy-tailed, so things like LQ with a very small q. And at the same time, some parameters in the space are continuous and some parameters in the space are discrete. And some parameters live in, I don't know, between 0 and 1. And I'll show like, and some parameters are sort of like in a combinatorial setting, I know, like a discrete vector of size 1,000,000. And I'll show strategies to address that. We don't have good general strategies for that unless you are very careful of how you design your model and your conditional distributions. But that's what I'll talk about tomorrow. If you go to models that look like this, but are just not log-concave, have heavy tails, then there's two main approaches that I think you can use. One is, of course, your recent work on prox regular models. And the other approach is to reformulate the Langevin process in a Riemannian manifold. So if you have, if you look at the Langevin diffusion, right now it's written in an Euclidean setting, but you could rewrite the diffusion in a Riemannian manifold, and then you would have a diffusion that moves. But the distances, and for instance, the gradient you are computing is not the Euclidean gradient, it's the gradient on the manifold. And that also provides a way of constructing a diffusion that is, so you can have something where you have like geodesic convexity in the manifold, even though you don't have it in the Euclidean space. So there's, but it's out there. I've seen it done in dimension 1.
Okay. Any other question in the audience? No? So yeah, you showed us images with MMAC estimations. Can you tell us a bit more how it is computed, since it is it comes up as an integral in the image space?
Yeah. So all you have to do is, so let's say I have this estimate here. So all you have to do is run your Markov chain and compute the average of the samples.
Yeah, but it's, it must take a long time, no? It
depends a lot on the model. So in 2014, I think, we was taking something like 2 months, then it went down to a couple of hours, and now for many models we're in a couple of minutes. And one of my PhD students is working on a paper where we're down to a couple of seconds, and so in a while I think it will be very competitive with optimization. So for many of these models, optimization will produce a solution in a second or something like that. I mean, that's my reference point. The problems I'm talking about are problems where optimization delivers a solution in a second, and we are now at a few minutes. I think, for this, in some examples, I have some more numbers tomorrow where I compare optimization with sampling. But now we're often in the order of a minute or something like that to get 10 minutes.
Okay. No, but you mentioned the issue of correlation within the Markov chain, and so you just use one Markov chain? No.
Just one Markov chain. What you need is to make the chain mix fast enough. So by using this approximation of the Langevin diffusion, if the problem is very ill conditioned, actually, if the conditioning number is really bad or just the Lipschitz constant is really large, then you have to take a small step size, otherwise the whole thing blows up. And then it's when you have computing times of the order of 10 minutes or half an hour, you have to do maybe 1 million iterations. But now we are working on a different way of discretizing the diffusion that is better. It's not our own work. I teamed up with a numerical analyst that specializes in stochastic methods, and he laughed at my algorithm and like, this is, like my daughter could do better than this. And his daughter is 6 years old. So now he just applied something he had from last year. He says, this is the state of the art, and it is orders of magnitude faster. Yeah.
So when you are trying to estimate the regularization parameter theta, so do you have any idea about the unicity of the solution? I mean,
yeah. So let's assume that I was in a denoising problem, so that I can get away with a few things. So then your model would write like a sum over all the pixel values. And then you would have something that looks, well, regardless of exactly what denoising problem it is, but it would look like, let's say, phi I of xi. Phi I of yi once I integrate out x. So I'll explicitly write xi here. And I'll make it clear that this depends on theta, my unknown parameter. And then here there will be an integral with respect to x. And it turns out that this sum will start averaging out anything that is not quadratic. And because this will be then divided by 1 over the sum of this with respect to y, this is sort of like self-normalized, and then you have a central limit theorem that kicks in, and it becomes quadratic. So there is some theory that says that if you have independent samples, then as the number of samples goes to infinity, provided that this is differentiable, which is just like a basic thing, then the likelihood will converge to a Gaussian likelihood centered around the truth, and the width of the Gaussian likelihood is given by the Cramer-Rao bound, so efficient information. In our case, it's not exactly like this, but it's not that far. We don't have pathological dependencies between the samples. We don't have long-range dependencies, things that would prevent the central limit theorem from kicking in. So when you do the experiment, there's ways of evaluating this at many points by brute force Monte Carlo integration, and you observe a Gaussian function. I mean, there are some cases where this probably won't happen, but in cases that are very regular and theta is scalar, it is a Gaussian function.
Thank you very much for your talk. Could you say a little bit more on how you compute Bayesian confidence region, and in particular how the sampling of the posterior probability helps you to do that precisely?
Yes. So what I have to do is make sure that what I have to do is find gamma. So what I do is I get all my samples, and then I find the value phi of x at each sample. And I look at that, and I look at the histogram of that, and then I take the 99% quantile, for instance, and by definition, that's giving me a value of lambda of gamma, such that 99% of the samples have a phi that is smaller than that, and 1% is higher. And that's how you get gamma. Now, that gives you a set in a very high-dimensional space. How exactly you probe that set to get uncertainty, that's a different problem. So we've done a few things that I'll talk about tomorrow, but one of the things that this is work with radio astronomers that are specialized in the imaging side, and one of the things they find really useful sorry, is to do this multi-resolution analysis. So they start with local structures that are very small. They go like for each pixel of the image, a structure of this size, how big would be the confidence interval? And then we move to larger scales. And you can do this in different ways, either directly from the samples, or you then take those pixels and amplify and attenuate their value until you exit the set, and that gives you like a way.
Okay, thanks. Any other question? No? Okay, so let's thank Marcelo again.